All right. Good morning, everyone. So there is only one announcement, and that would be the deadline for quiz 5, I think, today. So please make sure that you submit your quiz. Okay, so where are we in the course? So we have talked about the 4 concepts of operating systems. We talked about managing threads in an operating system. We then talked about scheduling threads, which is basically the topic of time sharing the processor. Now, this lecture is kind of like a last lecture that has something to do with time sharing the processor. And after that, we'll move on to the memory, and we'll start talking about how we can space share the memory. And then finally, we'll see how we can manage I/O system. So today's lecture is about real-time systems. So what we will see is a definition and features of real-time systems. We'll see how real-time operating systems are different from general purpose operating systems that we have seen so far. So there'll be some differences that we'll make that we'll highlight. To do so, we'll talk about desirable properties that a real-time operating system should provide, and then we talk about the differences. At the end of this lecture, we'll revisit scheduling for real-time systems, and we'll dive into the differences between what we've seen so far and what we have to do in a real-time system. And finally, we'll end this lecture with a discussion about managing multiprocessors for real-time systems and what challenges that brings in. If you remember, we started with uniprocessor. Even in general purpose operating systems, going from uniprocessor to multiprocessor brought us some challenges. Now we'll see how that's done in real-time operating systems as well. Okay. So what's the definition of a real-time system? Really, it boils down to having constraints on time and the temporal aspect of your system. So basically, the correctness of your system depends on its temporal aspect. Now, what does that exactly mean? We'll see. But one area here that we're always interested in systems performance. So when we talk about performance of a real-time system, we really what we really mean is our tasks meet their deadline. That's basically in one sentence what real-time systems boil down to. You have some timing constraints on your tasks, your threads, or your processes, and you want to meet those deadlines. Now, in general purpose systems, you care about average response time or average throughput for your system. In real-time system, you still might care about average response time or throughput, but that's not your main concern. Your main concern is that you want each individual task in your system to meet its deadline and its performance target. So even if the average is good, if you're failing like half of your tasks and the other half you're doing them super fast, your real-time system is a failed system, even though the average might be good. And the key property of a real-time system is its predictability. When you design a real-time system, you want it to be predictable. And well, that comes with that temporal aspect. So you want to provably have a system that guarantees that tasks meet their deadlines. Okay, there are three types of real-time systems, in big picture. There are soft real-time systems, there are hard real-time systems, and there are firm real-time systems. So what do we exactly mean by soft real-time system? That the soft actually goes with how tolerable it is to miss some tasks deadline. So in this figure, in this graph, on the x-axis I have time, and on the y-axis I have the value or usefulness of running this task. And let's say this is the deadline. Yep. So let's say this is the deadline. I should have had a mark here. Probably I can do it now. So basically this guy is the deadline here. Now, if you finish your task anywhere before its deadline, you get full value out of doing that task. The moment you miss the deadline, then the value that you get out of executing and finishing this task decreases. It doesn't. I mean, you can then compare it with other systems, but it doesn't right away go to zero, or it doesn't become negative. Now, compare that to a firm real-time system. A firm real-time system, again, your task has a deadline. And as long as you finish your task anytime before its deadline, you actually get the full benefit, full utility out of this execution. The value of finishing the task is high. The moment you miss the deadline, even if you finish it, you're not going to get any value out of executing it. And then finally, you have hard real-time systems where if you miss the deadline, then you're going to actually get a negative utility. Something really bad will happen, right, to your system. Now, just to make analogies, here you can see some examples of these systems. You have in the middle soft real-time system. On the right you have the hard real-time system, and then no real-time system at all. So I think this is the area that we're focusing with real-time system, because as you go here, there's no real-time system anymore. These are pretty much general purpose systems, right? When you're running like internet, video, audio, for these systems, you care about the response time of your system, but there's no explicit deadline for your tasks. You want them to be as fast as possible. For those of you who have done computer simulations, let's say for a new architecture that you have designed, you want to like for an FPGA, you want to see what happens inside. So if you run a simulation, then you really don't care when it finishes. Sometimes it takes 2 days, sometimes it takes 3 days, sometimes it takes 2 hours. You don't really have a deadline. You just run it until it finishes and gives you a result. Now compare that to real-time systems, starting with cruise control. So this is a soft real-time system. You want to get up to a speed, and that's important, but there is some leeway if you don't get there in time, or you want your cruise system to, you know, deactivate if you're in front of, another car is in front of you, and they push the brake and they stop. You want the cruise control system to deactivate. There is a deadline for that. It has to deactivate within some time, but then you also have the driver who could control the system even if the cruise control you know, is not meeting its deadline. There is still someone who can tolerate that. Now compare that to an electronic engine in a jet or in an airplane. There's nobody else sitting there, you know, fixing things for you inside the engine, and you have a deadline. And if you don't meet that deadline for doing the task that you have to do, then the engine could fail. People could die. Bad things could happen. And then something along these lines would be the firm real-time system. Okay. So takeaway from all of this is what we're concerned about in this lecture is that we have a bunch of tasks and they have a deadline. Each one of them has a deadline of itself. And then we want to meet those deadlines. Now, if we have a hard real-time system, we don't have any choices but to meet the deadline. If we have a soft real-time system, we should do our best to meet the deadline, to get the reward, to get the usefulness in the highest, in its peak before it starts degrading. And if you have a firm real-time system, you basically care about how many tasks you actually meet their deadlines, because if you miss the deadline, you don't get anything at all. You don't get negative reward, but you don't get positive either. So it's useless to finish that task once the deadline of that task is missed. Okay. Now, a theme of upcoming slides is that we're going to compare general purpose operating systems and real-time operating systems. And by comparing them, we're going to make a case that, well, because of this new constraint that we put for our tasks, we need to actually go back and redesign almost everything that we have talked about. Not all of it, but many of the things that we talked about to fit the paradigm of real-time systems. Now, this would include multitasking and multi-threading and scheduling, which has been the topic of our course for the past few weeks. As I said, the way it works in general purpose system, as we have seen, is basically through providing system calls, and then the problem with system calls is that it just there is no notion of deadline when it comes to system calls, and we'll see actually this in more detail. So we have to fix that when we want to do multitasking, multi-threading. Let's say you know, the way that we implemented locks through system calls. Like mute, you have a mutex, you lock that mutex, or you go to sleep on something. There is no guarantee when you're going to wake up, and that's bad, because in a real-time system you need predictability. You need to know when you wake up. Or let's say you create a thread, it's going to just become ready, and then we don't know when it's going to be running, when it's not going to be running. You don't have any certainty on anything, basically. So we have to fix that. And there is something wrong with the notion of system calls that we will also talk about. The other thing that is different, which you are now working on somehow in lab 3 about interrupt management, that also we have to address, because if interrupts happen, your system gets interrupted in the middle of a task. Now, if that task has a deadline that is coming and you just interrupt that task, do you know how long it's going to take to process that interrupt? Maybe your task will fail, meaning its interrupt. So again, we need to think about this in the context of real-time system and what we have to do. And finally, the synchronization primitives, which I sort of alluded to here, which is like if you're using locks or mutexes or semaphores, they're designed for a general purpose system where tasks don't have deadlines. Now, one of the things that I have been saying that I will talk about, I think we've seen it 2 or 3 times so far, is the notion of priority inversion. This is the lecture that we will talk about it in depth, what it means and what's its implications for a real-time system, and how we can address those implications and challenges. Okay, so to dive into more details of all the things that I just mentioned, let's just go through some desirable properties that a real-time operating system has to provide. Starting with predictability, which is what I talked about. Timeliness, again, we talked about. Fault tolerance is another aspect that is important, especially when you're talking about embedded systems. I mean, fault tolerance is important in any system, but usually real-time systems and embedded systems are designed for mission-critical systems, and fault tolerance is at most like it's one of the most important aspects of the system. We also need to design our system for the peak load, and then put this next to predictability. This actually means that even with the highest load in your system should act predictable in a predictable way, and it has to be maintainable. Your system. I'm not going to actually talk about these. We're going to focus mostly on these two, the first 2 ones, but these are also important aspects of real-time systems. If there was a course on just real-time systems, you might see a lot on these as well. Okay, now here's where we're going to dive into the aspects or challenges that we face in designing real-time systems. And where we're going to start is, as always, from the hardware. So let's look at the hardware that we have and see what aspects of this hardware are in line with what we want and what aspects are not in line with what we want. One of the important aspects that is not sort of in line with what we want is the I/O devices. So I'm going to actually here, this is one example. There are other examples as well, but here is one example. Let's say, I mean, we talked about DMAs. If you remember, when we were talking about data transfer between the CPU and the I/O device, we said that we don't want the CPU to be involved with every byte transfer. So we want the DMA engine to transfer data, and then we would keep CPU cycles for something more important. Now, what happens is, from the CPU to memory, there is a bus. This bus will be shared by the CPU to go to the memory and by the DMA. The DMA engine is going to take data from the device, put it in memory, or vice versa. It's going to transfer data from memory to the device. So the DMA engine is going to use this bus. The CPU is also going to use this bus now that it's not going to spend its cycles on transferring. It's going to go and take another task and run that other task while the DMA engine is working. Now, what's the problem here? The problem is sharing this bus with the DMA engine. When there is no DMA request being processed, this bus is entirely free for the CPU. So now let's say I'm running a real-time task, and this task has a lot of memory requests. Now, if this bus is not used by anybody else but the CPU, I can time and see how long it takes to run my task. And I could give some guarantee that I can run this task in, let's say, 10 microseconds or whatever. But what if there is a DMA request being processed? So when a DMA request is being processed, it's going to create memory request, and it's going to just use the bandwidth of this bus. And that could interfere with what the CPU is doing, and that could slow down the task that CPU is running. And that is actually against what we want with predictability. So it basically creates non-determinism. When you're running, you don't know if a DMA request is being processed or not. How big is that DMA request? And that is a non-deterministic event in your system, and you don't like it. So one way to deal with it is to just not have DMA. That's pretty much going too far, and that probably is not what you want to do because of all the bad things that we know about that, wasting CPU cycles and stuff. Okay, so if we want to have the DMA, what can we do? Well, one way that actually is done is something called time slice method. And what this is you time slice the bus between the CPU and the DMA. And what that means is that you basically isolate the bus. You give the CPU a portion of time on the bus where the CPU is the only user, and you give the DMA portion of the cycles or portion of the time that it uses the bus by itself. This brings you predictability. It may slow down your system, right? Because maybe you know, the CPU is not using all its share, or maybe DMA is not using its all share. But that's fine. This is actually the line that I want to make sure that everybody understands. It's fine for your system to be slower but predictable than faster but not predictable. So here we're sacrificing performance to get predictability. You will see actually this happening again and again and again in this lecture. Here is another example, caches. So you sort of saw one example of caches when we were talking about cache coherence, for example. The idea of having caches is you have this storage close to this data storage, very close to your CPU. It's very fast, but and it actually, for most applications that have data locality, it improves performance. But caches create great non-determinism in your system. The reason is you don't exactly know who ran before you. So you don't know if your data is cached or not. Even if you're the only one running, the data you have in your cache could be random based on the eviction policy that your cache has. When your cache gets full, some data should be evicted and some new data should come in. Now, how do you evict? There are different policies that we will talk about, but there might be some randomness in evicting a bunch of victims that have the same score for eviction. So that that randomness, with it comes non-determinism. And also, as I mentioned, maybe you ran and then there was a context switch, somebody else came, and that somebody else filled the cache with its own data. And now you come back, you have to fill the cache again. Or maybe that somebody else didn't use the cache at all. It was just computing stuff, and then went away, and now you come back and all your data is actually sitting in the cache non-touched. So based on each one of those scenarios, you get a different performance. Now, on average, having cache improves your performance. But if I look at any instance in time, your performance is non-deterministic, and that's bad for predictability. How do we solve this? Don't use caches. That's amazing for me to say, but it actually helps, and it actually happens in some real-time systems and embedded systems. So you just eliminate cache. That on average hurts your performance, but it makes your performance predictable. So when you start running your task, you know how long it's going to take. You can optimize it. You can guarantee stuff with it. You can say, this is how much it's going to take. And there is no non-deterministic event that could alter that fact, which is what you want in a real-time system. Okay, now let's revisit what I was just talking about, system calls, and see how they are creating challenges. And by the way, system calls were so far the interface between the application and the operating system, and that's how we were doing business. But the way that we have been handling system calls is kind of like not in line with what we want in a real-time system. Okay, so usually system calls in general purpose operating systems are non-preemptible. So the moment you call into the kernel by running SVC, the interrupts become disabled on your system. Which is kind of the case with our system as well, right? The moment you go to the kernel mode, interrupts are disabled. Now, okay, that's fine with general purpose operating systems, but what if I was running this, real-time task, and then this real-time task called a system call, and now I went to the system call, interrupts are disabled. The system, when you say interrupts are disabled, it basically means that your system call is not preemptible. You cannot preempt it. The only way to preempt your system call from continuing is either the system call itself returns, or you have some timer interrupt going off and saying, okay, that wherever you are, pause here, we'll come back to you. So none of that can happen. And well, that's bad, because what if the system call process to process that system call takes time and introduces delay? Well, you can't do anything about it. And what happens is that you can miss the deadline of the task that called into the system call. Or maybe not. Maybe another task that was not a real-time task called system call, and now we're in the system doing the system call, and a real-time task becomes ready to be executed with a deadline that is very close and very soon. But because we are processing the system call, we cannot context switch to this real-time task, and as a result, this real-time task could miss its deadline. Okay, so these are two scenarios that could happen. Now, how do we fix this? Well, an easy fix is, well, don't make your system calls preemptive, non-preemptive. Make them preemptive, meaning that don't disable interrupts inside your system call. That's easy to say. The moment you want to implement this, it has some corner cases that you have to make sure that is met. I think usually what happens is at the beginning of it, to just set up the system, you keep the interrupts disabled to just set up stuff. And then at some point you're like, okay, now I can be interrupted. Then you enable interrupts while still processing the system call, so that if some other high priority event happens in your system, you can actually catch it. What about interrupt handler itself? Well, interrupt handler is very in general purpose systems is very much like system calls. It's non-preemptive, it actually should remain non-preemptive in most cases. So we don't have that much leeway. It's a little bit more restrictive than system calls for us to enable interrupts while we're processing one, because you could end up having a situation where you have Stack Overflow. So you're processing one interrupt. If interrupts are still enabled, another interrupt could happen, and this interrupt could interrupt the interrupt handler. And then in the middle of that, another interrupt could happen, interrupting in the middle of the interrupt handler. And this could happen again and again and again, and you do a Stack Overflow. Basically, because you're just pushing on the kernel stack every time another interrupt happens, and this could be an infinite loop, and you don't get to process any of them, basically. Okay, so we kind of have to deal with it. How do we deal with this? So we're going to look at 3 solutions for interrupt handling. The first one is, well, let's do this. Let's disable all the interrupts and only keep the timer interrupt, because in essence, timer interrupt is the one that we care about the most because of the temporal aspect of our system. Let's have the timer interrupt enabled, but disable every other interrupt. Now, let tasks directly communicate with any I/O devices that they need, and let them transfer data by polling between them and the device. So basically, what we're doing here is let's eliminate interrupts from your system. Let's not have any interrupts. Like if somebody presses keys or moves the mouse or a network packet is delivered, we don't want to be interrupted by any of that. So disable all your interrupts so that you don't have any interrupt handler, basically. So the first solution is remove all the interrupt handlers. You only need one interrupt handler, and that's timer, because you need timer. You cannot get rid of timer. Because you need to be preemptive, and you have a real-time system, and you have deadlines to meet. So time is important. Keep the timer. Now, you still want to communicate with your I/O devices. Well, do that by polling. So don't do it with interrupts. Just any task that wants to, communicate with the keyboard, it starts pulling on the keyboard. If you want to use your mouse, you pull on your mouse. If you want to do networking, you pull on your network card. Okay, so this is one solution. Now this is actually the positive side of this is that we actually eliminated this non-determinism with regard to interrupts. Again, the non-determinism being that, let's say you had this real-time task running and then somebody pressed the keyboard. And then the deadline was very soon, but now you have to go to the interrupt handler and that introduces a delay that is non-deterministic to that task, and you might miss your deadline. So that was the problem. So we got rid of all the interrupt handlers because we have disabled them, but we still want to use the keyboard. So every task that needs to use I/O, they would pull on their I/O. So we have eliminated this unexpected device handling time, which is the plus side. That's what we had this solution for. What else? The communication also now between the device and the task is kind of like deterministic because you're pulling on your device. Let's say you can say, I'm going to wait for 5 milliseconds, see if any keyboard key has been pressed. So you can actually time it with your I/O devices because you're pulling on them. So that's also good. You can predictably work with your I/O devices because it's all in your control. The other good aspect of it from the operating system side is that you're not changing anything inside your kernel. If you need to add a new device, let's say you buy, new I/O devices, it's the task of the tasks to talk to the I/O device. Kernel doesn't do anything. Tasks are going to pull on I/O devices. So kernel is just sitting idle, not caring much about new devices. So what's the negative side of this? So the negative side of this is one, well, polling is not good, right? And it wastes CPU time. So performance is going to definitely degrade. Although we are getting predictability, we're really sacrificing performance by a lot. The other thing is that from the operating system side of things and programming side of things, we're putting a lot of burden on programmers, those who want to write tasks. So this basically means that every time you change your NIC card, for instance, or your keyboard or whatever, then the programmers should go back and rewrite their tasks because they put a lot of device-specific code inside their tasks. So, and that's basically not a good thing to do. What can we do then? Are there any other solutions? I got a question I will answer once I'm done with the 3 solutions. So solution number 2, let's keep interrupts disabled as solution number 1, basically getting rid of all the interrupts. Only keep the timer interrupt. So only be interrupted by timer. Now, instead of letting tasks handle I/O devices, each one of them by itself, instead bring that functionality inside the kernel. So write some kernel tasks that communicate with the devices, and then let them be invoked by timer interrupt. So every once in a while, so you could basically schedule these, we call them timer activated device routines. So these are either kernel tasks or kernel functions. Periodically, we can call them, and they would pull the devices to see if there is any new data, right? But this is done inside the kernel. I hope that makes sense. So it's different. So in solution number 1, tasks were doing their own I/O. Now we said that that was not that good because of all the things that the task has to do. Let's factor all of it inside the kernel, put them inside well-defined functions, and then periodically basically call these functions and routines to check on the devices. Now let's analyze this. This still has the good property of solution number 1. Mainly, we're eliminating the non-determinism that existed with having interrupts and interrupt handlers. We don't have it now. We're still doing the polling, so execution time of I/O requests is still manageable by us. We can say how long we want to poll and how frequently do we want to poll. So it's we have control over I/O devices. It's not like a random event happening. We're in charge of how long we want to spend on I/O. And the advantage over solution number 1 is that now hardware details are encapsulated inside the kernel. So the tasks don't need to care much about I/O devices, and they're not much burden on tasks. Now, what are the downsides of this? Well, the downside with polling is still there, performance degradation. The second one is now kernel is burdened by tasks, by devices. So every time you add or remove a new device, you have to redo your kernel. The third, which is a little bit more subtle than the other ones, is that you have introduced a lot of inter-task communication now, because previously in the previous solution, each task would do its own I/O, so there was no back and forth between kernel and tasks. Now we're back to the the general theme of general purpose operating systems. You do I/O inside kernel, and then you might send the data to another task, and then that other task might communicate with another task or come back to the kernel. So now we have communication. So there is communication between, at least between kernel and threads on I/O, compared to solution number 1. But overall, I think this is a better solution than number 1 from the programming side of view. Now, what is the third solution? And this third solution is actually a state-of-the-art. It's used in many systems. And if I'm not mistaken, lab 4 or 5, we are actually doing something very similar to this. So instead of disabling interrupts, so we're going to close this with this one. It's not the best solution that you can come up, but it kind of is a middle ground between the solution number 1 and 2 that are strict cases where you actually disable all the interrupts, and between the general purpose operating systems that interrupts could happen at any time and they could take as much time as they could possibly. So we want to find a middle ground. So what is this middle ground? You could enable interrupts, but make interrupt handling predictable. That's basically the message. So reduce the device driver. If you remember, device drivers are the ones that receive the interrupts, right? In that graph we had in the first slides. So make it as concise as possible and make it predictable. So it's very short, within few instructions. It will receive the interrupt, and then make it activate. So once the interrupt is delivered to the device driver, instead of processing it, the device driver will activate another task, another kernel task, to take care of this interrupt. Potentially, this other task could be given a deadline, a new deadline, saying that, okay, keyboard was pressed, I want it to be processed within this many seconds or this many microseconds. So create another task in your system, give it a deadline, and then leave the rest to the operating system scheduler to schedule tasks. Now, in this new manner, we have minimized interrupt handling to the bare minimum. We didn't process the interrupt fully, and we just created another task very much similar to other user tasks in our systems or any other kernel task in our system, and left it to the scheduler to make sure that everybody meets its deadline. So this eliminates busy waiting because now we're not polling, we're using interrupts. It actually doesn't make the kernel do the polling and then do all the dirty stuff with the devices. We still are using device drivers, so you don't need to modify the kernel. You have device drivers. Now, these are downsides, but not red. It's kind of like not that bad. So we are now communicating with devices, and that still involves inner task communication, very much similar to the general purpose and very much similar to this, to solution number 2. And we actually didn't make our system fully predictable because we still don't have any control over interrupts. Interrupts could happen. What we did was making the processing time of interrupts minimum, bare minimum, and we're not fully processing them. We're creating tasks to be executed later on once it's their turn. So we still have non-determinism, but we dramatically reduced the time and we made our system more predictable. So it's still unpredictable, but we can say like, oh, on average it takes this much and the variance is this much, for example, something along those lines. So we can say something about the execution time of our system, whereas previously we couldn't say anything because it was just arbitrarily long or arbitrarily short to deal with interrupts. Okay, let me now answer questions, or this one question. How would you deal with debouncing when polling? Do you need to introduce a delay which would waste CPU time? Can you elaborate more what you exactly mean by debouncing? It's the first time I'm hearing the term. So please clarify and I'll answer. Okay. Okay, let's move on to memory management. I'm going to visit lab 1 a little bit, what you did. So in general, oh, actually before that, so well, I'm going to sort of go over this slide pretty fast because we haven't yet seen it. So in few sentences, memory management in general purpose operating systems is very random and non-deterministic. The idea or the reason is you have virtual memory and then you have physical memory. And physical memory is limited, virtual memory is really big. Now, operating system has to space share this limited physical memory between processes. And in doing so, sometimes the physical memory gets full, and then you have to evict some data from one process to bring data from another process. And this eviction, very much similar to what I explained with caches, is sort of random. The other thing about it is that when you evict and you want to bring another page, another data, which we call them pages, back to physical memory, it could take a lot of time. And that by itself could also be non-deterministic, how long it takes to bring a file from hard disk back to memory, or how long it takes to evict a page from physical memory to hard disk to make room. So all of this creates a heck lot of non-determinism in your system. Now, what are the solutions? So again, we'll actually cover a lot about page table, translation, look ahead, look aside buffers, what are the pages. We'll cover them in depth. The purpose of this slide is just to say what you will see later on is good for general purpose. It's not good for real-time systems. So how do we do this? How do we deal with this? One way, one possible solution is to just avoid using virtual memory. Very much similar to the system that you're designing with labs. You don't deal with virtual memory. You're just using actual physical addresses. And that's pretty much very universal in embedded systems. That eliminates the use of virtual memory and makes it a lot more predictable to deal with memory. The other solution, the other thing that you could do when it comes, let's say you have to use virtual memory, to eliminate the non-determinism with evicting files, you could actually pin your data in the memory. You can tell the operating system that you're not allowed to evict this region of memory to the disk. The data should always remain in the physical memory. That is kind of like, it might be good if it's just one or two regions. If you're going to do that for the entire memory, then you could end up like with a system that is not working because you have more requests than resources available. And there is no way to pin all of them. Okay, so accidentally having multiple presses on I/O in a short period of time. Oh, that's what you meant with bouncing. So now I know bouncing. What was the question? How would you deal with debouncing? When polling, do you need to introduce a delay, which would waste CPU time? I still am not sure if I understand the question correctly, but the idea is, let's say if what you're saying could also happen, like you click something and then you hold your finger there and multiple keys are introduced. With polling, you are in charge of how long you want to poll and how many characters, let's say, you want to read. So you could say, I only want max time I want to stay in polling state is like 5 milliseconds, and the maximum number of characters I want to read is 1 character. So each one of these two happens first, you're going to terminate, or something along those lines. So you can make it predictable as you wish. So that's all I understand of that question. If there is more, we can actually discuss later offline. Okay. Now, here's the piece that you have seen actually when it comes to memory management. So when you were doing your lab 1, you were designing this memAlloc function, this memAlloc system call. You probably noticed, or you have noticed by now, that the performance of your system call, how long it takes for that to return, is kind of a random variable. It really depends on how fragmented your memory, for example, is to return or allocate memory by that memAlloc function that you had. So in essence, that's true for almost every general purpose memory allocator and memory manager. So usually memory allocators are non-deterministic. And the runtime really depends on how fragmented the memory is. The other thing about them is even in their responses, there is non-determinism. So you cannot have this, for example, this sentence, that if there is this many bytes unallocated, let's say if I have 1 megabyte unallocated memory, then if you request anything less than that, I'm gonna allocate it to you. You cannot make that guarantee. Why? Because of this. Here's an example. Let's say you call memAlloc for 3 bytes, you get 3 blocks or 3 bytes. Then you call for 4, you get 4. Then you free the first one, and now you have 6 blocks or 6 bytes available. So if somebody now asks for 4, which is less than 6, you may or may not be able to fulfill that request, depending on the fragmentation of your system. So there's no guarantee that if you have those many bytes available, you can fulfill that request because of the fragmentation. Because although you have 6 bytes or 6 blocks available, but they're not in a continuous region of memory, so you cannot allocate. And you don't want to, migrate your allocated memory here, because this P2, you might have other copies of it now, because this was a pointer pointing to this. So if you change it and change P2, you're not done, because you might have other copies of P2. You might have used P2 in other variables, and you cannot go back and change all of those variables. You don't know really. So you have defragmentation in other scenarios. We'll see it with memory, but it cannot happen here because I just explained why. Okay, so this again, non-determinism against predictability, bad. What should we do about it? So one extreme solution, get rid of dynamic allocation. Don't allow dynamic memory allocation in your system. And you would be surprised, actually many systems are this way. They don't have, if you're writing something for your like a embedded system and a system that has to be very predictable, there are chances that your system doesn't support dynamic memory allocation. So whatever memory you want, you have to statically allocate it. Let's say you really want to have dynamic allocation, you could create or divide your memory into blocks of the same size, and then allocate blocks. That way, you basically, so you eliminate the size parameter. So it's not like they can't say, give me this many bytes. They can say, oh, give me 1 block, 2 blocks, 3 blocks, or whatever. And as long as you have 1 block available, you can give them. So they can basically ask for one block at a time. So you give them one block, and as long as you have a free block, if somebody asks for give me a block, you can give them a block, right? It's kind of like changing this mem_alloc to just giving you 1 byte every time. So if you want 30 bytes, you have to call this 30 times. But then that's so inefficient if you do it 1 byte, 1 byte. So you basically put it in one big block and allocate blocks. That's kind of like, it's good in terms of predictability, but it's bad because you might not need the entire block, or you might need more than one block. So you have to call that again and again and again. So there is no actual solution, if I may. So would it be correct to say RTOS is simpler and easier to implement than general purpose operating system? That's a controversial question. I would say there are some real-time operating systems that are easier, but then you could have a real-time operating system designed for a specific system. That happens a lot. So like if you're a big company, you have a lot of resources and you have this really cool robot, you could design a specific operating system for your robot or for your product. And that probably would be easier to design than a general purpose operating system, probably. But then you also have general purpose real-time systems like FreeRTOS, for example, or ARM RTOS, or the Linux real-time operating system. So these are kind of like a general purpose real-time operating system. So it's a real-time system, real-time operating system, but general purpose. So it could serve many real-time systems. Those are, in my opinion, as hard to design as general purpose operating systems, because you don't exactly know what service your customer wants. So you put all the services that they might want, and then you let them customize the system for their need. Yeah, okay, so I guess I said the second solution first, so you don't allow dynamic allocations, or you just do by fixed blocks. Another thing that you have taken for granted in general purpose operating system when it comes to programming languages is the notion of recursion, writing recursive programs. You could now hopefully understand why that's not a good idea in a real-time system to have recursion or allow recursion, because it could take forever. We don't know how long it's going to go, how many levels of recursions it's going to have, and it might go against giving us any time bound on execution time. Okay, here are some examples of real-time programming languages like real-time Java, concurrency, Euclid, and so on and so forth. I actually did search last term to see if I can get any of these and work with them. These are mostly academic projects, as far as I know. I think some of them are more general than academic, but it's kind of like a research topic to come up with these programming languages for real-time systems. I think practically you probably have a real-time system you want to design, and then you pick a programming language, let's say C or C++, but then you make sure that you don't use the things that you shouldn't be using, because you're designing your system. your coding for your system. It's very customized to your need. So you just make sure that you don't do the things that you shouldn't be doing, which is error prone, but it is what it is. Okay. Well, so now we're back. We're kind of in a state to talk about scheduling real-time systems, which in my opinion is one of the main parts of real-time system, considering that what distinguishes real-time systems from general purpose systems is that temporal aspect. You have a deadline, you want to meet that deadline. And that, well, as we saw, has a lot to do with how we handle interrupts, how we handle system calls, what kind of architecture we use, how we're doing memory management. It touches all those aspects. But more so, it touches how you're time sharing the CPU. So this is also very, very important. If you want to meet your deadline, you have to run that task in a timely manner. The question, can you briefly re-explain why solution 3 for system calls is the best? I'm still a bit confused. I actually didn't say it's the best. So I just said it's the middle ground. It's something in between disabling all the interrupts and letting interrupts be handled the way they are handled in general purpose systems. So we picked a middle ground, which boiled down to minimizing the time it takes to initially handle the interrupts. And then we don't fully process interrupts, we create tasks, and then we leave it to the scheduler, which we were going to talk about next, to schedule those tasks to be handled. So let's say somebody presses a keyboard, presses a key. Right now in lab 3, what you're going to do is you immediately process the entire thing, right? You create that message, you send it to KCD, you display the character on the UART out the serial port. So you do all of that. So you fully process your request. Instead, you could imagine, okay, a key was pressed. So I create another task, like I call create task, to create another task that would go and process all of this. And then I give it a deadline or something. And now that task goes back to the ready queue and becomes like a task like any other task. So the time that it takes is just to create that task, to deal with the interrupt. I'm not going to fully process it. And then eventually that task will be processed based on the scheduling system. So again, I'm not saying that's the best way. It's just a middle ground. It's usually used in many systems. If you really want predictability, if you're designing, an engine or something, then you go with solution 1 or 2. And that the downsides of those two doesn't really matter in many cases. So the downsides of, having to deal with devices inside your task, many times it doesn't really matter. You're fine because you're designing a customized system for your own system. You're the designer of the hardware. You're also programming it, so you're fine. Or even with the second one, you might be also fine. You might also have resources to put and design kernel and then maintain that kernel as you add or remove devices to your system. So if predictability is the most important thing in your system, you cannot, sacrifice that. Then you go with solution 1 or 2. If you could satisfy it by some margin, if you have some flexibility, then you go with solution number 3. Okay. Now, scheduling. Okay. So how much time do I have? I have 10 minutes. We'll see how much I can cover. So general purpose schedulers are system oriented. They just care about like the average system throughput. As I said, with real-time systems, you need to think about minimizing the worst case time for each task. So, and we have seen it again and again and again and again, predictability not equal fast computing. We actually sometimes, sacrifice performance for predictability. Now, real-time tasks are usually represented by bunch of characteristics. What are they? So we usually say they have an arrival time. So okay, let's start with this. So real-time tasks have types. One of the types that we care a lot are periodic tasks. So a periodic task is a set of jobs. So I'm actually defining jobs now. So far I've talked about tasks, now jobs. So a periodic task is a set of jobs that arrive at fixed periods. Now, we're going to assume that we know the worst case execution time of each job, and they're the same. So we're going to present it with E, and each one of them has a hard relative deadline from when it arrives until it has to be finished. That's its deadline. Now that would be D, and it has to be less than P, right? P is when the new one comes. So the deadline for the previous one has to be before the new one comes. You don't want them to now compete with each other, each one of your tasks. If you don't mention D, then it's we assume that D equals P. So the deadline is basically the period, the relative deadline. A utilization of a task, of a periodic task, is E divided by P. Basically, what does it mean? E was the runtime of each job, and P is the period of arrivals. So every P unit of time, I get one new job that would take E time units to run. So how much this task is going to utilize my CPU, if I run this task, basically meaning if I run every job of this task, it would mean that every P unit of time, I'm going to be busy with E units of time. So that's how much one task, one periodic task, is going to utilize my CPU, E divided by P. Now here is an example. This is one task that we're showing it with period 7 and runtime 4. Period 7 means that it's going to arrive a new job, and all of the jobs within a task are symmetric. So they're all the same. So all the jobs within one task, they're all the same. They have the same deadline, they have the same execution time, worst case execution time, and so on and so forth. So basically, inter-arrival time between new jobs is going to be 7. That's your period. And each one of them is going to take 4 units of time to execute. So this is the most important thing that you have to fully understand. So periodic tasks, that's how we define them. We also have other types of tasks. You might have aperiodic tasks. So the difference between periodic and aperiodic is that the aperiodic ones, they arrive randomly. So one task comes, and it doesn't have any hard deadline. It's kind of very similar to general purpose tasks. So it just comes at some point. It doesn't have a deadline. You have to do it if you have time, right? It doesn't have any deadline. It doesn't have any hard deadline. You could have a sporadic tasks. So these guys come randomly, but they have deadline. They have hard deadline. So that's it. So periodic tasks, which we define them as being a set of jobs, set of symmetric jobs, aperiodic tasks that are very similar to general purpose tasks that we have seen so far, and then sporadic tasks. Basically, there is only one that comes at some point, and it has a deadline that we have to meet. Now, tasks could be independent. They could have interdependencies. Your system could be preemptive or non-preemptive, meaning that you could be able to preempt your tasks or not preempt them. Now, for the purpose of this lecture, we're going to look at independent tasks and preemptable tasks. So we are able to preempt our tasks, and there are no dependencies between them. Later on, I'll talk about relaxing these assumptions. Okay, now probably this would be the last thing I will talk about, terminology of real-time scheduling. So we have a static scheduling. Basically, what that means is priority of each task does not change over time. So that's a static scheduling. So if a task has a priority, it will always have that priority over time. It's not going to change at any point in time. An example, rate monotonic. I will talk about it actually. The second class of a scheduling is dynamic scheduling. Now, with dynamic scheduling, priority of each job doesn't change over time, but priority of tasks could change. So basically, the unit that we're assigning priority to is jobs in dynamic scheduling instead of tasks. So with this first one, each single periodic task has a bunch of jobs. So all of the jobs of one task, they all have the same priority, and their priority never changes. It's the same as the task's priority. Let's say if the task's priority is 10, all the jobs within this task will have priority 10 every time they arrive. With this one, we don't assign any priority to task. We assign priority to jobs. So now each task has jobs, infinitely many. They come periodically, and each one of these jobs has a priority. And as long as that job is in the system, its priority is not going to change. Now, a new job comes off the task. It could get a new priority, which is different than the previous job. And another job comes from this task. It could get a new priority that is different than the previous job. So the jobs have priority that is fixed over time, but different jobs within the same task could get different priorities. The third class is fully dynamic scheduling. This basically means, again, we're going to assign priority to each job rather than tasks, but then the priority of a job could actually change over time. So your job could start with priority 10, and at some point in time, some event happens, and its priority changes to 11 or 12 or 13. So we're able to change the priority of each individual job. So that's a static, dynamic, and fully dynamic scheduling policies. Now, one thing, do I have slides for? Yeah, so all three are in online scheduling policies. So overall, we have online scheduling and offline scheduling. offline scheduling, we're not interested in. So with offline scheduling, you basically, before you run your system, you know what tasks are going to come, and you create a table. You say, this task should run first, this task should run second. So everything is actually offline. You create your table. The schedule is predetermined before you run your system. You know your tasks, you know what you want to do with your system. That would be offline scheduling. We're not actually interested in that. With online scheduling, your system is online. You schedule online, meaning that you don't make any assumptions on what tasks you have, how many tasks you have. They could come and go, and then you just assign them priorities as you go in runtime. Okay, so with online scheduling, we have these three categories: static, dynamic, and fully dynamic. With offline, it's just simple, like you know everything about your system, you schedule your system, and that's pretty much it. Okay, I'm over time. I couldn't finish the last three bullets. They're important, so I'll cover them in the next lecture. So thank you for those who attended the lecture. Thank you to those who watched the lecture later on. As always, please take care of yourself, stay healthy, and talk to you later. Bye-bye.